Hello everyone. This video is roll center part 6. During a constant speed turn, when there is a large lateral acceleration among the lateral load transfer elements, the gyroscope precession effect will be examined in detail from the principle to the application, and what effect it has on the vehicle during the turn or the bump or rebound movement of the wheel. In the previous video, E0073, roll center part 5, I explained the roll motion of a rigid body, the roll angle of the sprung mass, and the influence of tire stiffness on the transfer of lateral load. In addition, I explained the angular momentum to understand the gyroscope precession effect and briefly explained how the gyroscope precession effect affects a vehicle when it turns. In this video, I will explain the principle of gyroscope precession in detail, using the behavior of a rotating body in response to torque input as an example, and then explain real-life examples, such as a bicycle and a spinning top. Next, I will explain the gyroscopic precession effects on a vehicle for rotating parts of the engine and transmission, bumps and rebound, and wheel and tire. Finally, I will explain the exact expression of lateral load transfer. All of the vehicle-related content explained in this video is about steady-state cornering with a constant speed. In this case, the roll angle and yaw rate are constant. I will explain cases other than steady-state cornering in a subsequent videos. I have a quiz for you. The picture on the left shows the moment when the right front wheel of the vehicle hits a bump. Which of the following correctly represents the direction of precession? Number 1. The precession effect occurs along the vertical z-axis. Number 2. The precession effect occurs along the negative z-axis. Number 3. The precession effect occurs along the positive x-axis. Number 4. The precession effect occurs along the positive y-axis. Choose one correct answer. Let's look at the precession motion of a gyroscope. The figure on the left shows the motion of a gyroscope connected to the center axis of a support stand, which is aligned with the vertical axis, the z-axis. The gyroscope is connected to a ball joint on the top of the vertical stand, which can rotate in all directions. Regardless of the rotation of the gyroscope, a force mWg is generated in the vertical direction by the self-weight mw of the gyroscope. The force generated by the gyroscope due to its own weight can be expressed using vectors as in equation 1. In equation 1, vector k is a unit vector along the z-axis. The torque generated by the self-weight of the gyroscope about point O can be expressed using vectors as in equation 2. If the gyroscope does not rotate with high angular velocity omega w, the ball joint at point O cannot support the torque Rmwg generated by the weight mwg of the gyroscope, as shown in equation 2, and the gyroscope will fall to the ground. At this time, the torque can be expressed as a scalar quantity as in equation 3. However, when the gyroscope rotates at a high speed, the gyroscope does not fall to the ground, but rotates about the axis Z, which is called the precession motion of the gyroscope. Let's find out how this phenomenon occurs. Here, a gyroscope, represented by a green circle, is rotating at high speed with a constant angular velocity omega w. The coordinate system shown here is the coordinate system fixed to the gyroscope. The z-axis is perpendicular to the ground, the x-axis is aligned with the axis of the gyroscope, and the y-axis is perpendicular to the gyroscope shaft. mw represents the mass of the gyroscope, omega w represents the angular velocity of the gyroscope, I represents the mass moment of inertia of the gyroscope, and Lw represents the angular momentum of the gyroscope. For simplicity, the mass of the gyroscope shaft is ignored. All objects rotating from a stationary state have an angular momentum, which has a direction and magnitude, and they tend to maintain that state. To change this, a torque is needed. As seen in the previous video, the angular momentum of the gyroscope can be expressed as equation 5, referring to equation 4 derived in the previous video. As shown in equation 5, the direction of angular momentum Lw is the same as the direction of angular velocity omega w, so it coincides with the direction of the position vector r passing through the central axis of the gyroscope, as shown in the figure. Even if it is a rotating gyroscope, the fact that it receives a force due to its own weight, mwg, does not change. However, a gyroscope that rotates at a high speed has angular momentum, as shown in equation 5, and according to the law of inertia, it tries to maintain the same direction and rotation. However, when the force due to its own weight, mwg, acts, the motion of the gyroscope will change because a torque is generated centered on point O. How will it change? To find out, let's look at the yellow shaded area. The yellow shaded area is a circle on the x-y plane and has a radius r. As shown in the figure, if you release a gyroscope that rotates rapidly at a constant speed about the x-axis, the gyroscope will not fall to the ground, but will perform a rotational motion called precession along the circumference of the yellow circle centered on the z-axis, as shown in the figure. The reason the gyroscope does not fall is because it has an angular momentum vector Lw generated by the high-speed rotation of the gyroscope, as shown in equation 5. To make the explanation easier, let's make two assumptions. As the first assumption, the angular momentum of precession is smaller than the angular momentum of the gyroscope, so it is ignored. As the second assumption, the axis of the gyroscope is considered to be horizontal at the moment of precession, as shown in the figure. The torque of the gyroscope can be expressed as equation 7 by referring to equation 6, which we looked at earlier. It is an expression of Newton's second law for angular motion. The force due to gravity on the gyroscope can be expressed as equation 1 using the unit vector k. The position vector from the origin to the center of the gyroscope wheel is r, and the gyroscope load acts in the vertical downward direction, so the torque generated by gravity can be expressed as the product of these as in equation 8, and the direction of action is the horizontal direction perpendicular to these two vectors, as shown in the figure. In equation 8, vectors I, j, k are unit vectors that coincide with the x, y, and z axes, respectively. Angle d phi in the figure is a very small angle, but it is shown large for explanation. As shown in equation 7, the torque tau causes a change in the angular momentum of delta d Lw during the unit time delta t. On the other hand, if the rotation speed omega w of the gyroscope is constant, the magnitude of the angular momentum does not change, as shown in equation 5. Recalling that angular momentum is a vector quantity with magnitude and direction, we can see that the only thing that can change the angular momentum without changing the magnitude of the angular momentum is the direction of the angular momentum. As we have seen, dLw has the same direction as the torque, tau, and is perpendicular to Lw. Also, angular momentum Lw is coincident with the rotation axis, and the direction of the axis can be found by applying the right-hand rule. Thus, the direction of interaction among the angular momentum Lw, the infinitesimal angular momentum dLw, the gyroscope self-weight mwg, and the torque tau remains constant regardless of the precession angle. Therefore, the gyroscope continues to move in the direction in which the torque tau acts and undergoes a precession motion rotating about the z-axis. Let's find the angular velocity of precession omega p. The angular velocity omega p of precession is the rate of change of angular pi with respect to time, so it can be expressed as equation 9 and is called the precession rate. We start with equation 5 obtained above. The angular momentum vector Lw expressed by equation 5 can be expressed as a scalar expression, as equation 10. The torque tau w generated by the self-weight of the gyroscope can be expressed as equation 8. Also, if equation 7 obtained above is rearranged into a scalar expression for dLw, we can obtain equation 11. the torque vector tau w of equation 8 can be expressed as a scalar expression, as equation 12. If we substitute the scalar quantity of the torque, tau w of equation 12 into equation 11, we can obtain equation 13 for the infinitesimal angular momentum dLw. Continuing, from the geometric relationship between the angular momentum vector Lw and the infinitesimal angular momentum dLw in the figure, we can obtain equation 14. If we rearrange equation 14 in terms of d pi, we can obtain equation 15. By substituting dLw from equation 13 and Lw from equation 10 into equation 15, we can obtain equation 16 representing d pi. Finally, by rearranging equation 16 in terms of dt, we can obtain equation 17 for the precession rate omega p. Furthermore, from equation 17, the torque tau w can be expressed as the product of the mass moment of inertia times the gyroscope angular velocity omega w and the precession rate omega p, as in equation 18. From equation 17, we can understand the characteristics of precession motion. First, the numerator tau w of equation 17 is the active torque due to the gravitational field, as shown in equation 12. However, the denominator on the right side of equation 17, I omega w, is the angular momentum generated by the mass of the rotating gyroscope and exists regardless of the gravitational field. From equation 17, we can see the characteristics of precession. As the active torque tau w increases, the precession rate increases. On the other hand, as the mass moment of inertia of the gyroscope increases or the rotational speed omega w increases, the precession rate decreases. In addition, we can see from equation 17 that the mass is not related to the precession rate. This is because in the last term of equation 17, the torque Tw includes the mass, and the denominator I also includes the mass, so they cancel each other. Also, as shown in equation 19, the product of the precession angular velocity and the angular velocity of the gyroscope has a value equal to the active torque Tw divided by the mass moment of inertia I. Here, I will explain the direction of precession from the gyroscope motion in the figure. In the figure on the left, the axis direction of the torque tau is perpendicular to the force mwg and the position vector r. Meanwhile, since the gyroscope is rotating counterclockwise when viewed from point O, the angular momentum Lw of the gyroscope can be expressed in the direction of the arrow in the figure on the left according to the right-hand rule. An easy way to find out the direction of precession is to remember that when the starting point of angular momentum arrow and the starting point of the torque arrow are placed at the same point, the tip of angular momentum arrow always follows the tip of the torque arrow. If we apply this principle to the case of the figure on the left, the direction of precession is clockwise when viewed from above, as shown in the figure. In the figure on the right, the gyroscope is rotating in the opposite direction to the figure on the left. In this case, since the gyroscope is rotating clockwise when viewed from point O, the direction of the angular momentum of the gyroscope is opposite to that in the figure on the left according to the right-hand rule. The direction of the torque is the same as the direction of the left figure, since the direction of mwg is the same as the left figure. If we match the starting point of angular momentum arrow and the starting point of the torque arrow in the same way as before, it will be as in the right figure. In this state, the direction in which the end point of angular momentum arrow follows the end point of the torque arrow is the direction of the precession. It is counterclockwise when viewed from above. Therefore, we can see that the direction of the precession changes when the rotation direction of the wheel changes. From now on, we will understand the precession motion of the gyroscope through various examples. As the first example, let's consider the case where a transient torque is applied to the bicycle wheel. The left figure shows a person with his feet fixed on the ground holding the axle with the rotating bicycle wheel horizontally. The bicycle wheel is rotating about the positive y-axis. Therefore, the direction of the angular momentum of the bicycle wheel is the positive y-axis. In this state, if we want to change the direction of the bicycle wheel in any direction, we need to apply a torque to the system because the direction of the angular momentum of the bicycle wheel changes. Let's consider the case where a person applies a torque to the bicycle wheel by pushing the right hand pointer forward and pulling the left hand point C backward, as shown in the top view on the right. If we represent this in the side view, it will look like the lower right figure. In this case, since the right hand pointer is pushed and the left hand point C is pulled, the direction of the torque axis is the positive z-axis. As shown in equation 7, the person applied the active torque tau only for a time of dt, thereby changing the direction of the angular momentum of the bicycle wheel about the positive z-axis. How will the bicycle wheel behave in this case? If the bicycle wheel is stationary and not rotating around the y-axis, the bicycle wheel will continue to rotate about the z-axis due to the active torque tau even after the time dt has passed. If a person intervenes and stops the rotation about the z-axis, a reactive torque in the opposite direction to the active torque initially applied to the person's hand will occur for time dt. However, if the bicycle wheel rotates at high speed about the y-axis, the wheel will behave differently when the same torque is applied because it has angular momentum. So how will the bicycle wheel behave? In order to understand the behavior of the bicycle wheel, we need to analyze the angular momentum vector dLw, which represents the amount and direction of change in angular momentum as seen above. As explained above, the direction of the angular momentum vector dLw is parallel to the positive z-axis, which is the torque axis at point C, and parallel to the negative z-axis at point A. This is a direction perpendicular to the angular momentum of the bicycle wheel and is consistent with the precession direction. If a torque is applied to the bicycle wheel for only a time dt and then stopped, the precession motion also occurs for only a time dt and then stops. Therefore, when a person pushes with his right hand and pulls with his left hand, the axis of rotation of the bicycle wheel does not remain stationary while rotating in the x-y plane as in side view 1, but precession motion occurs, and as in side view 2, the right hand holding the bicycle wheel axle receives a downward force, and the left hand receives an upward force. An easy way to figure out the direction of precession is to remember that, as explained earlier, when the starting point of angular momentum arrow and the starting point of the torque arrow are placed at the same point, the tip of the angular momentum arrow always follows the tip of the torque arrow. Let's take another look at the direction of precession using this. Let's look again at the precession motion of the gyroscope for the transient torque. As before, pointer in the left figure here represents the right hand position and point C represents the left hand position. If we transiently pull the left hand with the force Fwc for time dt and push the right hand with the force Fwa and stop, the reference axis of the transient torque tau w that occurs at this time will coincide with the positive z-axis. The momentum axis is aligned with the rotation axis of the gyroscope, so it is the positive y-axis. Therefore, the direction of the infinitesimal momentum dLwc is perpendicular to the angular momentum axis and parallel to the positive z-axis, which is the torque axis. Since the direction of the infinitesimal momentum dLwc coincides with the precession direction, the precession motion of the gyroscope will rotate in the direction of a circle passing from point C through point D and passing through point A for infinitesimal time dt. As shown in the equations a 1 and a 2, the absolute values of these couple forces are the same. If we explain this based on the displacement caused by the couple force, it can be expressed as shown in the figure on the left. At point A, the couple force Fwa acts transiently, generating a displacement dWa, and at point C, the couple force Fwc acts transiently, generating a displacement dWc and then stopping. At the same time, the couple forces FPA and FPC, which generate precession motion, transiently occur in the direction of precession rotation for time dt, so that pointer moves in the negative z-axis direction by dpa, and point C moves in the positive z-axis direction by dpc and then stops. After this, all forces acting on the system except for the force supporting the gyroscope's gravity disappear. Let's understand the gyroscopic precession through the movements of point A and C. In the right top view, if you push point A and pull point C, the direction of the torque is the positive z-axis direction. In the front view shown at the bottom right of the screen, this is the direction in which the active torque is directed. On the other hand, the direction of angular momentum is the positive y-axis direction. Since the endpoint of the angular momentum arrow always rotates toward the endpoint of the torque arrow, the precession of the bicycle wheel is the direction in which it rotates based on the positive x-axis. Therefore, the bicycle wheel rotates about the positive z-axis along the blue arrow as shown in the right front view. Since a person supplies active torque only for a fixed time dt, the precession rotation is completed after this time, and all forces except the force due to the weight of the bicycle wheel disappear, but the deformation angle due to the torque does not return to the original position and remains rotated. In conclusion, if you rotate the bicycle wheel shaft about the positive z-axis for a fixed time by applying an active torque, the bicycle wheel performs a precession movement and the bicycle wheel shaft rotates about the positive x-axis for a fixed time. When the active torque of the bicycle wheel disappears, the precession motion also disappears, and the axis of the bicycle wheel continues to rotate with the angular momentum direction changed. The figure on the left shows the expanded view of points A, B, and C of the side view. In this state, if a torque is applied by pushing the left hand and pulling the right hand in the opposite direction of the given torque, the bicycle wheel returns to the initial state. The behavior of the bicycle wheel that we have looked at so far is exactly the same as the behavior of the vehicle wheel when the vehicle turns. Here, the person is the driver, and as shown in the top view, pushing the right hand and pulling the left hand to apply torque is the same as the action of applying torque to the vehicle to turn left. Just like the bicycle wheel, when the vehicle turns left, the active torque axis acting on the wheel in the front view is the positive z-axis, and the angular momentum axis is the positive y-axis, and it is directed toward the center of the vehicle's turning circle. Since the tip of the angular momentum arrow always rotates toward the tip of the torque arrow, the precession of the vehicle wheel is the direction of rotation based on the positive x-axis. As the vehicle continues to turn, since torque is continuously supplied, the vehicle wheel tries to continue to perform precession motion. Therefore, the vehicle wheel generates an overturning moment that tries to rotate about the positive x-axis along the blue arrow as shown in the right front view. We will look at the overturning moment generated in the vehicle in more detail later. Let's explain the changes in the bicycle wheel that we looked at earlier in an easy-to-understand way. In the figure, capital letters represent the inertial coordinate system fixed to the ground, and small letters represent the local coordinate system fixed to the bicycle wheel. In the local coordinate system, the y-axis coincides with the center line of the bicycle wheel axis. As shown in the figure on the left, the inertial coordinate system and the local coordinate system coincide before applying torque. When a person pushes with his right hand and pulls with his left hand to apply torque to a bicycle wheel that is rotating at high speed for a certain period of time, as shown in the local coordinate system of the figure, the y-axis rotates by a certain angle with respect to the z-axis, so the direction of the angular momentum changes. When the direction of the angular momentum changes with respect to the z-axis, our nature simultaneously generates a torque that tilts the bicycle wheel in the direction of precession, and if we represent this using the local coordinate system, we can represent it as shown in the figure. Therefore, the final posture of the bicycle wheel is a combination of the torque given by the person and the torque reacted by nature, and if the final posture is expressed in the inertial coordinate system, it becomes a shape that has rotated a certain angle about both the z-axis and the x-axis, as shown in Figure 3. As shown in Figure 3, a person transiently generated a torque about the z-axis and rotated the bicycle wheel a certain angle about the positive z-axis, but at the same time, the torque generated by nature reacted to this and applied at the same time, so that it also rotated a certain angle about the positive x-axis. When the posture is as shown in Figure 3, the bicycle wheel rotates at the original speed and all torque disappears. Since this result is not very intuitive, it is quite difficult for us to easily know the direction of the precession. However, although it is not intuitive, if we remember that when the starting point of angular momentum arrow and the starting point of the torque arrow are placed at the same point, the end point of angular momentum always tends to rotate toward the end point of the torque, we can find the direction of the precession. This time, we will look at a case where a continuous torque is applied to a system with a frictionless rotatable base plate. Initially, a person standing on a base plate holds the shaft of a bicycle wheel that is rotating at high speed horizontally with both hands. In this state, base plate is not rotating. It is assumed that the base plate can rotate relative to the ground without friction. The difference from the previous example is that the person is standing on the floor plate and the floor plate can rotate with respect to the ground without friction. Initially, there is no force that generates torque except the force due to the weight of the bicycle wheel, so if the person maintains the original posture, no new force is generated in the system. In this state, if the person raises the right hand point C and lowers the left hand point A to apply an active torque and maintains the size of this torque, let's see how the system behaves. Since the active torque acts clockwise from the direction of the person's view, the active torque axis is the positive x-axis. Meanwhile, since the bicycle wheel is rotating around the positive y-axis, the direction of the angular momentum is along the positive y-axis. Since the tip of the angular momentum arrow always rotates toward the tip of the torque arrow, the reference axis of the direction of the bicycle wheel's precession movement is the negative z-axis. Therefore, precession movement is performed, and the bicycle wheel rotates about the negative z-axis along the blue arrow as shown in the upper right of the right figure. Since the floor plate on which the person is standing can rotate without friction with the ground, all objects behind the floor plate, including the person, rotate in the precession direction. As long as the person continues to maintain the active torque in the state where the right hand point C is raised and the left hand pointer is lowered, the precession rotation continues without being completed. This time, let's look at how the system behaves if, contrary to the previous case, a person raises pointer of the right hand and lowers point C of the left hand to maintain active torque. Since the direction of rotation of the wheel is the same as before, the direction of angular momentum does not change. Since the active torque acts counterclockwise from the direction seen by the person, the active torque axis is the negative x-axis. Since the tip of the angular momentum arrow always rotates toward the tip of the torque arrow, the reference axis of the precession motion of the bicycle wheel is the positive z-axis. Therefore, the bicycle wheel performs precession motion as shown in the upper right of the right figure, and rotates about the positive z-axis along the light blue arrow. Since the floor plate on which the person is standing can rotate without friction with the ground, all objects on the floor plate, including the person, rotate in the precession direction. As long as the person maintains the active torque in the state of raising pointer of the right hand and lowering point C of the left hand, the precession rotation does not complete and continues. In this way, you can see that the direction of precession also changes to the opposite direction when the torque axis changes to the opposite direction. Let's examine the precession motion of the gyroscope for the continuous torque again through the displacement of points A and C. As before, pointer in the left figure here represents the right hand and point C represents the left hand position. If we continue to lower the left hand with the force FWC and raise the right hand with the force FWA, the reference axis of the continuous torque tau W that occurs at this time coincides with the negative x-axis. The momentum axis coincides with the rotation axis of the gyroscope, so it is the positive y-axis. Therefore, the direction of the infinitesimal angular momentum dLWC is perpendicular to the angular momentum axis and parallel to the torque axis, the negative x-axis. Since the direction of the infinitesimal angular momentum dLWC coincides with the precession direction, the gyroscope performs the precession motion and rotates along the direction of the circle passing through point D from point C. Since the floor plate on which the person is standing can rotate without friction with the ground, all objects on the floor plate, including the person, will rotate in the precession direction. If we explain this based on the displacement caused by the couple force, it can be expressed as shown in the figure on the left. If the couple force FWA at point A and the couple force FWC at point C are continuously applied, a torque of tau W is generated, and displacement dWA at point A and displacement dWC at point C are generated. As long as the active torque is maintained in this state, the precession rotation is not completed and continues. As a next example, let's look at the precession effect in the case of riding bicycle with the handlebars free. Since the bicycle wheel rolls forward, the direction of the angular momentum of the wheel is perpendicular to the wheel when going straight and is horizontal to the left of the driver. What happens if the driver tilts the bicycle to the left in this state? In this case, the torque is generated by the driver's body tilting motion, and since the center of gravity is tilted to the left when viewed from the driver's side, the torque generated by the total weight of the bicycle and the person acts counterclockwise from the driver's perspective. Therefore, the torque axis is the negative x-axis direction toward the rear of the bicycle, as shown in the side view. Since the tip of the angular momentum arrow always tends to rotate toward the tip of the torque arrow, the direction of the precession movement of the bicycle wheel tends to rotate toward the torque axis pointing to the rear of the bicycle, and the rotation axis is the positive z-axis direction. Therefore, the precession movement occurs, and the front wheel of the bicycle tends to rotate along the positive z-axis along the blue arrow. Accordingly, if the body is tilted to the left, the front wheel of the bicycle will rotate to the left. Conversely, what happens if the rider leans the bike to the right in this state? In this case, the torque is generated by the driver's body leaning motion, and since the center of gravity is tilted to the right when viewed from the driver, the torque generated by the total weight of the bike and the person acts clockwise from the driver. Therefore, the torque axis is in the positive x-axis direction toward the front of the bike, as shown in the side view. Since the tip of the angular momentum arrow always tends to rotate toward the tip of the torque arrow, the direction of the precession motion of the bicycle wheel tends to rotate toward the torque axis pointing to the front of the bicycle. The rotation axis is in the negative z-axis direction. Therefore, the precession motion occurs, and the front wheel of the bicycle tends to rotate around the negative z-axis, following the blue arrow. Accordingly, if the body leans to the right, the front wheel of the bicycle will rotate to the right. Here we will look at the angular motion of a top. So far, we have analyzed the case where the physical quantities related to the gyroscope motion are perpendicular to each other. If the central axis of the top is aligned with the vertical z-axis and the center of gravity of the top is on this central axis, the top can spin while maintaining an upright posture. However, if the central axis is not aligned with the vertical z-axis and the top spins, the torque due to the weight of the top will be applied because the straight line connecting the point of contact with the ground and the center of gravity of the top is not a vertical line. If the momentum axis of the top is tilted, the calculation is difficult, so it is better to calculate the momentum component in the horizontal direction. The physical quantities related to the precession are expressed centered on the center of gravity CG of the top, as shown in the figure on the right. Since the top is tilted by angular theta with respect to the z-axis, the horizontal component of the momentum is Lw sine theta. Momentum Lw sine theta can be seen as the top acting as a gyroscope when its momentum is reduced by the amount of sine theta multiplied. From the center of gravity Cg, the weight mg of the top acts vertically downward, generating torque tau w. The torque at this time is the horizontal distance from the z-axis multiplied by the weight mg of the top. When the torque tau is calculated from the figure, it becomes our mg sine theta, as shown in equation 20. The infinitesimal angular momentum dLw is perpendicular to the angular momentum Lw sine theta as the same direction as the torque tau, and can be expressed by equation 21. Since the tip of the angular momentum arrow always tends to rotate toward the tip of the torque arrow, it performs a precession circular motion along the blue arrow in the figure, and the precession axis is the positive z-axis. From the geometric relationship in the figure, equation 22 can be obtained. By substituting tau w of equation 20 into equation 21, the infinitesimal angular momentum dLw can be expressed as equation 23. If dLw of equation 23 is substituted into equation 22, equation 24 can be obtained. If dt of equation 24 is moved to the left side and rewritten, equation 25 can be obtained. The left side of equation 25 represents the precession angular velocity. Therefore, equation 26 can be finally obtained. In equation 26, omega p represents the precession angular velocity of the top. You can see that all the equations here are identical to the equations for the gyroscope derived earlier. Engines, transmission components, and electric vehicle motors all rotate. This time, we will learn about the precession effect of these powertrain rotating components in the longitudinal engine and transmission. First, let's assume that all powertrain components rotate about the positive x-axis. The engine, transmission, and motor all rotate about the positive x-axis that faces forward. Therefore, as shown in the figure, the angular momentum axis faces forward. When the vehicle turns left, torque due to the vehicle rotation occurs about the positive z-axis. Since the arrow end of the angular momentum vector always tends to rotate toward the arrow end of the torque vector, the precession direction occurs about the negative y-axis, as shown in the figure. Therefore, the phenomenon of the front sprung mass being lifted occurs. Conversely, when turning right, torque occurs about the negative z-axis. On the other hand, since the rotation direction of all powertrain components does not change, the direction of the angular momentum does not change. Since the arrow end of the angular momentum vector always tends to rotate toward the arrow end of the torque vector, the precession direction occurs with respect to the positive y-axis as shown in the figure. Therefore, the phenomenon of the rear sprung mass being lifted occurs. Now, let's look at the case where the entire powertrain components rotate about the negative x-axis in the longitudinal engine and transmission. The engine, transmission, and motor all rotate about the negative x-axis, which points rearward. Therefore, as shown in the figure, the angular momentum axis points rearward. When the vehicle turns left, torque due to the vehicle rotation occurs about the positive z-axis. Since the arrow end of the angular momentum vector always tends to rotate toward the arrow end of the torque vector, the precession direction occurs about the positive y-axis, as shown in the figure. Therefore, the phenomenon of the rear sprung mass being lifted occurs. Conversely, when turning right, the torque occurs about the negative z-axis. On the other hand, since the rotation direction of all powertrain components does not change, the direction of the angular momentum does not change. Since the arrow end of the angular momentum vector always tends to rotate toward the arrow end of the torque vector, the precession direction occurs about the negative y-axis, as shown in the figure. Therefore, the phenomenon of the front sprung mass being lifted occurs. What happened in the case of the transverse engine, transmission, and motor? The engine in the figure is a side view from the left side of the vehicle. The transverse engine, transmission, and motor all rotate about the negative y-axis, which is toward the right side. First, let's assume that all powertrain components rotate about the negative y-axis, as shown in the figure. Therefore, the angular momentum axis points toward the negative y-axis. When the vehicle turns left, the torque due to the vehicle rotation occurs about the positive z-axis. Since the arrow end of the angular momentum vector always tends to rotate toward the arrow end of the torque vector, the precession direction occurs about the negative x-axis, as shown in the figure. Therefore, the phenomenon of the right side sprung mass being lifted occurs. Conversely, when turning right, the torque occurs about the negative z-axis. On the other hand, since the rotation direction of all powertrain components does not change, the direction of the angular momentum does not change. Since the arrow endpoint of the angular momentum vector always tends to rotate toward the arrow endpoint of the torque vector, the precession direction occurs with respect to the positive x-axis as shown in the figure. Therefore, the phenomenon of the left sprung mass being lifted occurs. The right side of the vehicle being lifted in a left turn or the left side of the vehicle being lifted in a right turn has the effect of reducing the roll angle of the vehicle's sprung mass. What happens if the rotation direction of the powertrain components is reversed? Unlike before, let's assume that the entire powertrain components rotate about the positive y-axis. They rotate in the same direction as the wheels and tires. Therefore, as shown in the figure, the angular momentum axis points toward the positive y-axis. When the vehicle turns left, torque due to the vehicle rotation occurs about the positive z-axis. Since the endpoint of the angular momentum vector always tends to rotate toward the endpoint of the arrow of the torque vector, the precession direction occurs about the positive x-axis, as shown in the figure. Therefore, the phenomenon of the left sprung mass being lifted occurs. Conversely, when turning right, the torque occurs about the negative z-axis. On the other hand, since the rotation direction of all powertrain components does not change, the direction of the angular momentum does not change. Since the endpoint of the arrow of the angular momentum vector always tends to rotate toward the endpoint of the arrow of the torque vector, the precession direction occurs about the negative x-axis, as shown in the figure. Therefore, the phenomenon of the right sprung mass being lifted occurs. The left side of the vehicle lifts when making a left turn, or the right side of the vehicle lifts when making a right turn, which has the effect of increasing the roll angle of the vehicle's sprung mass. In this way, the roll angle of the sprung mass during a turn can increase or decrease depending on the direction of rotation of the transverse powertrain components. There are two main types of gyroscopic precession effects on wheels. Both are caused by changes in the direction of the angular momentum. In the two figures here, the green arrows indicate the direction of the angular momentum axis of the wheel. The first is the change in the direction of the angular momentum axis that occurs when the suspension link rotates around the swing center during a bump or a turn. In this figure, the angular momentum axis of the wheel changes when a vehicle traveling straight encounters a bump. This case of the wheel rotating about the x-axis can occur not only due to a bump, but also due to the roll motion of the body when the vehicle turns. When the angular momentum axis of the wheel rotates about the x-axis in this way, the precession movement of the wheel occurs around the z-axis. Therefore, it affects bump steer. On the other hand, when the vehicle turns, the direction of the angular momentum axis of all rotating vehicle parts constantly changes around the z-axis. When the direction of the angular momentum axis of the wheel changes around the z-axis, the precession movement of the wheel occurs in the direction of rotation outward around the x-axis. This causes an overturning moment at the wheel and tire. These two phenomena can be analyzed separately because both the cause and the effect occur in different degrees of freedom. Let's analyze them in detail to see why these phenomena occur. First, let's look at the case where one wheel of a vehicle is bumped. The figure shows the rear view of the front wheels of a driving vehicle. The left wheel is not bumped, but only the right wheel is bumped. Let's assume that the right wheel is bumped and the wheel is tilted as shown in the figure. The right wheel rotates around the swing center. If the arm length from the wheel center to the swing center is Re, the torque that rotates the right wheel when bumped can be obtained as in equation 27. The axis of this torque is in the negative x-axis direction, and it is the direction coming out of the screen. This torque can also be expressed using equation 18, which was obtained previously, using the mass moment of inertia of the rotating part, the precession angular velocity, and the wheel angular velocity. Since the endpoint of the angular momentum arrow always rotates toward the endpoint of the torque arrow, the right wheel performs a precession movement to rotate to the left. Therefore, bump steer occurs, and the direction of bump steer is a left turn. This time, let's look at the case where both wheels of a vehicle are bumped. The figure shows the rear view of the front wheels of a driving vehicle. This is the case where both the left and right wheels are bumped. Since we have seen that bump steer occurs in the case of the right wheel bumping, let's look at only the left wheel this time. Let's assume that the left wheel is bumped and the wheel tilts as shown in the figure on the left. The left wheel rotates around the swing center. If the arm length from the wheel center to the swing center is Re, the torque that rotates the right wheel when bumped can be obtained as in equation 27. The axis of this torque is in the positive x-axis direction, and it goes from the outside to the inside of the screen. This torque can also be expressed using equation 18, which was obtained previously, using the mass moment of inertia of the rotating part, the precession angular velocity, and the wheel angular velocity. Since the end of the angular momentum arrow always rotates toward the end of the torque arrow, the right wheel will perform a precession movement to rotate to the right. Therefore, bump steer occurs, and the direction of the bump steer is a right turn. If the amount of bumps on the left and right are the same, the bump steer effect cancels out each other and disappears. Here is the picture showing the wheels and suspension swing arms when the vehicle is turning left, as seen from the rear. When body roll occurs in a left turn, and the angular momentum axis of the wheel rotates about the x-axis as shown in the picture, the axial direction of the active torque is toward the rear of the tire as shown in the picture. That is, the direction coming out of the screen. Meanwhile, the angular momentum axis direction of the left and right wheels is consistent with the positive y-axis direction. Since the endpoint of the angular momentum tends to rotate toward the endpoint of the torque axis, the left and right wheels perform a precession movement in the same direction about the positive z-axis. Since the precession movement about the positive z-axis is consistent with the left turn direction of the vehicle, both wheels tend to rotate about the positive z-axis. This rotation direction is counterclockwise in the top view. On the other hand, here is the picture showing the wheels and suspension swing arms as seen from behind when the vehicle is turning right. When body roll occurs during a right turn, when the angular momentum axis of the wheel rotates about the x-axis as shown in the picture, the axial direction of the active torque is toward the front of the tire as shown in the picture. In other words, it is the direction going inward from the screen. Meanwhile, the angular momentum axis direction of the left and right wheels is consistent with the positive y-axis direction. Since the endpoint of the angular momentum tends to rotate toward the endpoint of the torque axis, the left and right wheels perform a precession movement in the same direction about the negative z-axis. Since the precession movement about the negative z-axis is consistent with the right turning direction of the vehicle, both wheels tend to rotate about the negative z-axis. This rotation direction is clockwise in the top view. From now on, we will learn about overturning torque, which affects the transmission of vehicle lateral load. Among the rotating parts of a vehicle, all parts that rotate in the same direction as or opposite to the rotation of the wheels and tires affect the transmission of lateral load. The torque that tries to rotate the wheels and tires around the x-axis is called overturning torque. All parts that rotate in the same direction as the rotation of the wheels and tires generate overturning torque toward the outside of the vehicle turning. On the other hand, all parts that rotate in the opposite direction to the rotation of the wheels and tires generate overturning torque toward the inside of the vehicle turning. The figure on the left shows a vehicle turning left at a constant speed within a certain radius. Since the direction of the turning vehicle keeps changing, the direction of the angular momentum of the vehicle wheel also keeps changing along with the vehicle. The figure on the right shows one wheel of the vehicle as a representative. When the vehicle turns left, all parts that rotate in the same direction as the wheel, including the vehicle wheel, receive this torque tau W. The direction of the torque tau W is the positive z-axis, and as shown in the figure on the left, it is the direction coming out of the screen. The direction of angular momentum L is toward the rotation axis of the vehicle wheel, so according to the right-hand rule, it points toward the inside of the turning vehicle, that is, toward the center of the turn. Since the end point of the arrow of angular momentum always tends to rotate toward the end point of the arrow of torque, it tends to rotate about the positive x-axis. Accordingly, an overturning torque tau p is generated in the same direction as the angular velocity omega p of the precession. Therefore, all parts that rotate in the same direction as the wheel, including the wheel, generate an overturning torque that tries to rotate outward in the same way. The overturning torque that tries to rotate outward about an axis parallel to the x-axis increases the load transfer to the outside. This time, let's look at the case of right turn. The figure on the left shows a vehicle turning at a constant speed within a certain radius. Since the direction of the turning vehicle keeps changing, the direction of the angular momentum of the vehicle wheel also keeps changing along with the vehicle. The figure on the right shows one wheel of the vehicle as a representative. When the vehicle turns right, all parts that rotate in the same direction as the wheel, including the wheel, receive the same torque tau W. The direction of the torque tau W is the negative z-axis, and as shown in the figure on the left, it is the direction from the outside to the screen. The direction of the angular momentum L is the direction of the rotation axis of the vehicle wheel, so according to the right-hand rule, it faces outward from the turning vehicle, that is, outward from the center of the turn. Since the arrow end of the angular momentum always tends to rotate toward the arrow end of the torque, it tends to rotate about the negative x-axis. Accordingly, an overturning torque tau p is generated in the same direction as the angular velocity omega p of the precession. Therefore, all parts that rotate in the same direction as the wheel, including the wheel, generate the same overturning torque that wants to rotate outward. The overturning torque that tends to turn outward about an axis parallel to the x-axis increases the outward load transfer. As we have seen, whether the vehicle is turning left or right, all parts of the vehicle that turn in the same direction as the wheels generate an overturning torque toward the outside of the turn, thereby increasing the outward load transfer. If we combine all the load transfer terms that we have looked at in this video, E0074, and the previous video, E0073, the exact load transfer equation can be expressed as equation 28. All of these terms are expressed in terms of torque. The first term, tau c, represented by equation 30, is the first term in equation 29 and is the torque calculated by treating the entire vehicle as a rigid body. The second term, tau s, represented by equation 31, is the second term in equation 29 and is an additional torque calculated by reflecting the lateral displacement of the sprung mass center using the roll center. Tau o, represented by equation 32, is the third term in equation 28 and is an additional torque calculated by reflecting the lateral displacement that occurs when the tire receives lateral force. Tau p, represented by equation 18, is the fourth term in equation 28 and is an additional torque that reflects the gyroscopic precession effect caused by the rotation of the wheel. When reflecting the tau p, it is important to note that the torque tau p for the parts of the vehicle that rotate opposite to the wheels and tires must be added as a negative term on the right side of equation 28. If all four terms are reflected, the lateral load transfer equation can be expressed as equation 33. Furthermore, if we divide both sides of equation 33 by mh, we can obtain equation 34. The remaining tau due to aerodynamics and tau y due to your motion will be covered in a subsequent videos. Let's find the answer to the quiz. The picture on the left shows the moment when the right front wheel of the vehicle hits a bump. Which of the following correctly expresses the lateral load transfer? The red arrow in the figure indicates the direction of the angular momentum of the wheel. Since the wheel is rolling forward, the angular momentum axis is in the positive y-axis direction. In the figure, the direction of travel of the vehicle is in the positive x-axis direction entering into the screen. As shown in the figure, the wheel is the right wheel of the front wheel, and when bumping, the torque acts with respect to the negative x-axis. Therefore, as shown in the figure, the active torque axis is in the direction coming from the screen when bumping. Since the tip of the angular momentum vector arrow tends to rotate toward the tip of the torque vector arrow, the angular momentum arrow pointing to the positive y-axis in the figure indicates the precession effect of trying to rotate toward the tip of the active torque arrow pointing to the negative x-axis. Therefore, it makes a movement to rotate about the positive z-axis. As a result, bump steer occurs and the direction is a left turn. You can see that the answer to the quiz is number 1. Let me summarize what this video covered. The principle of the gyroscopic precession is explained. When a continuous torque is applied to a rotating object, the angular momentum axis changes and precession motion occurs. The principle for this is that, first, the rotating object has an angular momentum vector. A torque is needed to change the direction of the angular momentum vector. When a continuous torque is applied to a rotating object and the direction of the angular momentum vector is changed, precession motion occurs continuously. When a transient torque is applied to a rotating object, the angular momentum axis rotates at a constant angle about two axes, the torque axis and the precession axis. After the direction of the angular momentum is changed about the two reference axes, all torque disappears and the object continues to rotate with the angular momentum changed. I explained the examples of the precession motion of a gyroscope that occurs in real life. The first example is a bicycle. If you lean your body to the left while riding a bicycle without holding the handlebars, the precession occurs in the left-hand direction and the front wheel turns to the left. If you lean your body to the right without holding the handlebars, the precession occurs in the right-hand direction and the front wheel turns to the right. If you turn the handlebar to the left, the precession motion occurs to lean the bicycle to the right. If you turn the handlebar to the right, the precession motion occurs to lean the bicycle to the left. This phenomenon is the same as the precession motion that occurs in all parts that rotate in the same direction as the wheels when the vehicle turns. The second example is a top. If the rotation center axis of the top is upright, the precession motion of the top does not occur. If the center of gravity deviates from the center axis, a torque due to the weight of the top occurs. The generated torque causes the precession motion of the top. The gyroscopic precession of the rotating parts of the vehicle powertrain is explained. In the longitudinal engine and transmission, the parts rotate around the longitudinal axis of the vehicle, so the precession motion that lifts the front or rear wheels occurs when turning depending on the rotational direction of the parts. If the rotational direction of the parts changes, the direction of the precession motion changes when turning. In the transverse engine and transmission, the parts rotate around the transverse axis of the vehicle. If the direction of rotation of the parts matches the direction of rotation of the wheels, the load transfer to the outer wheel increases when turning. If the direction of rotation of the parts is opposite to the direction of rotation of the wheels, the load transfer to the inner wheel increases when turning. The gyroscopic precession of the vehicle wheel and tire is explained. The vertical motion of the wheel that occurs during bumps and rebounds causes precession motion. The vertical motion of the wheel causes bump steer. When the right wheel bumps, the bump steer is in the left direction. When the right wheel rebounds, the bump steer is in the right direction. The precession motion of the wheel and tire during a turn is explained. When turning, all wheels and tires receive a torque whose angular momentum continuously changes. The torque that occurs at this time causes precession motion in the wheel and tire. Precession motion causes an overturning moment about the forward-facing axis. All vehicle parts that turn in the same direction as the wheel cause an overturning torque toward the outside of the turn. All vehicle parts that turn in the opposite direction to the wheel cause an overturning torque toward the inside of the turn. Finally, in the previous video E0073, Vehicle Roll Center Part 5, the calculation of the lateral load transfer for large lateral forces and lateral accelerations, and this video, we explained how to accurately represent the lateral load. There are 4 factors that affect the lateral load. These are the rigid body model load transfer, the lateral displacement of the center of gravity, the displacement of the tire contact point, and the gyroscopic effect. There are also other factors that are not included here, such as aerodynamics and yaw. These will be explained in future videos. If you watch the previous videos, you can learn about various fields of automotive knowledge and enjoy a more in-depth understanding of future videos. In the last video, E0072, the 4th part of vehicle roll center, I explained how to find the roll center of a suspension using force vectors and how the height of the roll center affects the driving performance. In the latest video, H0073, the 5th part of vehicle roll center, I explained the lateral load transfer considering the roll center and tire stiffness. In addition, I also explained the principle of angular momentum and the brief introduction of the gyroscopic precession effect applied to vehicle load transfer. The following video will be Roll Center Part 7. I will explain the lateral load distribution of suspension. Please hit the thumbs up and catch the brand new videos by free subscription. So what are you waiting for? See you at next videos. Goodbye, guys.